Okay, good morning, everybody. All right, my name is Ben Cassese. I'm the AAS media intern, and I will be emceeing this morning's press conference. So it is Wednesday, Tuesday, January 9th. It is 10:15 a.m. in New Orleans for the 243rd meeting of the American Astronomical Society. This morning's press conference is titled Exoplanets and Brown Dwarfs. I'm joined by Susanna Kohler, the AAS press officer, and Carrie Hensley, the deputy AAS press officer. We'll have four presenters today. There will be approximately five associated press releases with their presentations. The videos of yesterday's press conferences are now public as well, so we encourage you to look at those. The ground rules for today remain the same as they were yesterday and will be for the rest of the week. Each of our presenters will go in order, giving their presentations. We ask that you not applaud between their presentations and save that and your questions for the end. We'll do one joint Q&A session for everyone once all the presentations are over. If you are attending on Zoom or watching on YouTube, we encourage you to ask your questions via the Zoom chat, where Susanna and Carrie will help read them out at the end of the presentations as well. So I'll just introduce each of our speakers before handing it over to them. Up first, we have Genaro Suarez of the American Museum of Natural History. He'll be giving a talk titled Extrasolar Worlds Exhibit Exotic Sandy Clouds at the Equator. After that will be Austin Rothermich from the CUNY Graduate Center, using citizen science to identify new ultracool benchmark systems. Then we'll have Jackie Faherty, also of the American Museum of Natural History, giving a presentation titled JWST Indicates Auroral Signature in Extremely Cold Brown Dwarf. And then finally, we have Dakotah Tyler of the University of California, Los Angeles, who will be giving a talk titled WASP 69b's Escaping Atmosphere is Confined to a Tail, at least 7 planetary radii. Okay, so I'll invite our first presenter up to begin the conference.
Oh, screen sharing.
Thank you.
Yeah.
Good. Okay. Perfect. So, hi everyone. I'm Genaro Suarez, a postdoc at the American Museum of Natural History, working in the Brown Dwarfs in New York City research group. And I'm going to present a result that we recently published about the distribution of sandy clouds or dust clouds in extrasolar worlds. So in a few words, we found that the equator of extrasolar worlds is cloudier than the poles, as we can see in this image. And we obtained this result by analyzing a number of objects called brown dwarfs. But what are brown dwarfs? So brown dwarfs are the link between very low mass stars and giant planets. They are substellar and superplanetary objects in mass, but they have insufficient mass to shine like stars. And here we have cold objects on the right and hot objects on the left. And from these three brown dwarfs categories, the L type are the hottest brown dwarfs, T dwarfs are cooler objects, and white dwarfs are the coldest known brown dwarfs. The result that I mentioned is focused on L dwarfs, where those clouds can form, and we can observe those clouds in their photospheres. For this, we use data from the archival of the retired NASA's Spitzer Space Telescope. Before James Webb, Spitzer was the only facility able to observe the signature produced by those clouds in brown dwarf atmospheres. So we can see here an example of the observations that we analyzed. This is a spectrum that tells us the brightness of a body at different wavelengths. So this is a spectrum at mid-infrared light, which is beyond the light that a human eye can observe. And we can see this form that is the signature produced by sandy clouds in these atmospheres. So the presence of this feature in the spectra is indicative of the existence of sandy clouds in these objects. So we analyze a number of these features to know if these objects have or not sandy clouds. So we focus on a sample of brown dwarf for which we know their inclination, which means that we know if we are observing the equator or the poles or other inclination of these objects. So to understand this concept of inclination, we can think of a concert that we are in a huge stadium. So imagine that we are the artists. So we can see the faces of people in front of us in the front seats, but we will see the legs of people in the higher seats. So something similar for brown dwarfs, we can see the equator or we can see the poles of the brown dwarfs depending the object that we are observing. So we have here in the top objects that are viewed from the equator. In the bottom, we will see objects observed from the poles. And also in the horizontal axis, we will see here objects with different amount of clouds. We will see objects with more clouds on the right, with less clouds on the left. And as an auxiliary axis here in color, I will show different color for the objects just to have an idea or if the object is redder or bluer than expected. So we found this amazing correlation between the three quantities, between inclination, cloud cover, and color. So this means that worlds view equator on are cloudier, and because they are cloudier, we see a redder color. So an analogy or an example to understand or to assimilate this result, we can think of a sunset on the Earth. So in a cloudy sunset, we will see a redder color compared to a sunset with a clear sky. So something similar for brown dwarfs, but in this case, the color change is from the equator to the pole. This is another figure to another way to interpret this result. So imagine that we have a extrasolar world. So if we observe this object from the equator, the object will be redder than expected. But if we observe the same object from a higher latitude, we will see a more normal color. But if we see the same object again from close to the poles, the object will be bluer and the spectrum will be very different compared to when observed from the equator. So this indicates that the appearance or the color diversity of these extrasolar worlds is highly influenced by the viewing inclination of these objects. And this is my main conclusion. I would like to thank my collaborators and the institution that made this result possible. Thank you.
Okay, perfect. Well, hello, everyone. My name is Austin Rothermich. I am a third-year graduate student at the CUNY Graduate Center and also at the American Museum of Natural History, working with the Brown Dwarfs in New York City Research Group, along with Genaro Suarez. And I'm really excited to tell you guys all about some amazing discoveries that have come as a result of citizen scientists lately. Before we dive into that, I want to take you back to this brown dwarf comparison plot that Genaro showed us. And we're again going to be focusing on the brown dwarfs in the middle. So as Genaro told us, brown dwarfs are substellar objects. They don't fuse hydrogen in their cores like normal stars do. And as a result, once they form, they're actually just going to slowly cool over time throughout the brown dwarf spectral sequence. One big result of this is that we have a huge degeneracy between mass, temperature, and age. So if you just have the temperature of the object, it's very difficult to tell anything else about the object going forward. This means that for your typical brown dwarf just traversing the galaxy in solitude, your brown dwarf is actually very mysterious. It does not want to give away any of its secrets, and as hard as you try, it just won't tell you anything. But if we now notice that there happens to be another object moving near it, and if this is a main sequence star, you can actually find out a lot more information about this main sequence star than you can the brown dwarf. For example, this star shown here on the right, we can tell it has an age of about 10 billion years, We know it has a somewhat solar metallicity, and we can tell the difference in carbon to oxygen in its atmosphere. These are all things you would never get from the brown dwarf on its own. But now if we can tell that these two objects forms together, well, now you can apply those same properties of the star to the brown dwarf, breaking that degeneracy, and now you have unprecedented access to the information in that brown dwarf that you would never have before. And that is the power of these benchmark systems. Moving forward, you can then use this to test and constrain theoretical models on both formation and atmospheres, and you can begin to use this to help ground your analysis on other brown dwarfs that you find in the field that don't have a host star with them. So in order to find some more benchmark systems, we turned to the citizen scientist project Backyard Worlds Planet 9. Backyard Worlds started in 2017 out of a desire to discover the nearest and coldest systems to the solar system. What Backyard Worlds presents to volunteers are shown on the right-hand side of the screen here. These are called flipbooks. These are images from the WISE Space Telescope in the mid-infrared. And each flipbook covers the same portion of the sky, but over multiple years. Any object that is closer to our solar system, as we would expect brown dwarfs or some low-mass stars to be, we should see their motion quite clearly. And so volunteers will look through images such as this, and if they notice anything moving in the images, as I have circled and highlighted here on these flipbooks, they can mark them, and those coordinates are then sent to the core science team for further verification. The Backyard Worlds project right now has just over 175,000 volunteers, and it spans over 150 countries, and more than 10 million individual WISE images have been classified to date. And this is actually where I get my start too. Back in 2017, when I was an undergraduate, I stumbled upon Backyard Worlds one day as I was really bored, and I fell in love with it. And especially due to the love and care of the core science team, I chose to pursue this as my career, and I now stand before you as a PhD candidate in this field. So while these volunteers are looking through different images, especially in different visualization tools created for example, by citizen scientist Dan Castleton, and this is a tool known as WiseView, which is publicly available. Volunteers will notice that there are sometimes very bright moving objects in the field of view that they're looking at. And an eagle eye viewer might also notice that there is a smaller, fainter, more orange reddish object that is moving along with it similarly. The volunteers can flag these separately from their normal brown dwarfs so that we can follow up on these more carefully and verify if they are in fact moving together. Using this technique, Backyard Worlds has identified 89 new benchmark systems. Our host stars for these systems span a wide range of spectral types, all the way from solar-like stars of about F6 down to some of the coldest and lowest mass stars of the M9s. And our companions similarly span a huge range of spectral types from M7 all the way down to the coldest, some of the coldest brown dwarfs, T9s. This represents an increase of brown dwarf companions to solar-like stars of 42%. And we also more than double the known extremely wide brown dwarf population. We also were able to follow up on 32 of these brown dwarf companions with near-infrared spectroscopy from about 1 to 2.3 microns, as is shown on the right-hand side here. Many of these observations were actually aided by citizen scientists. Not only were several of them able to participate in our observing runs, but they were actually able to control the telescope and actually take some of the data that you see before you now. And these companions have a wide range of properties. We see things that have indications of low surface gravity, indicating potential youth. We see things that look potentially metal poor, indicating that they might be older. And we have some objects that have a little bit more dust in their atmosphere than you might expect. And a lot of the diversity that we see in these objects is actually the same type of object that Genaro was telling us about. So one possible explanation for all this diversity does appear to be that there could be these sandy silicate clouds that are in their atmospheres, driving some of their colors and properties different. So these are great follow-up targets for future surveys so that we can try to do the same investigation as Genaro has done, but now aided by the same properties of the host star to better inform ourselves of what's happening in their atmospheres. And so as a summary, through the Citizen Science Backyard Worlds project, we have increased the known brown dwarf population of solar-like stars by 42%. We have more than doubled the known extremely wide brown dwarf companion separations. And this is total 89 new benchmark systems. And before I go, I just want to say thank you to all the citizen scientists that have helped and participated. While there are well over 100,000 volunteers, there is a much smaller, closer-knit community that spends a huge amount of time and a lot of energy to help discover these incredible worlds. And so without all of their wonderful work, I would not be standing here before you. Thank you very much.
No, that's your presentation.
Yeah,
very good.
Okay. Hello, everybody. My name is Jackie Faherty, and I'm an astronomer at the American Museum of Natural History in New York. We're the trifecta here for you. I'm a founder of the Brown Dwarfs in New York City Research Group, a co-founder of the Backyard Worlds citizen science project that you heard about. And today I get to tell you the story of brown dwarfs, and specifically a discovery that we have made using the James Webb Space Telescope focused on a very cold brown dwarf. So Genaro and Austin described the brown dwarfs to you, but they were focused on the warmer ones. I'm going to be very focused on the coldest class of brown dwarfs. Those are the Y type of brown dwarfs. They have surface temperatures that range from like the setting you put the convection oven at Thanksgiving to cook the turkey to a cold day on the North Pole. And my team, which includes Genaro and Austin here, one time in JWST cycle 1 to go after 12 of the coldest brown dwarfs that exist in order to go under the hood and look at what was in their atmospheres. They're extremely analogous to Jupiter. They have clouds that are very interesting. At the coldest compact, we're not talking about silicate clouds like Genaro was saying. We're talking about water ice clouds. We're talking about chemistry that's a very intriguing analog to Jupiter. We got spectra for 12 different objects. I am going to show you spectra for 2 of them right now. Their names are 1935 and 2220. It's named after their coordinates. I'm sorry, I don't have a better name for them, but hopefully you'll fall in love with those coordinates today. 1935 is an object that was actually discovered by citizen scientist Dan Castleton. He brought it to our attention on the Backyard Worlds team. We fell in love with the potential of that object, and it got onto our JWST target list. This other object, 2220, was discovered by NASA's WISE team several years before 1935. But I'm going to show you the 2 of these together because they're very similar to each other. They're spitting distance away within 50 light years, both of them. Their temperatures are about 400 degrees Fahrenheit, which is like what you bake your cookies at, like a really good cookie. That's the temperature. And their masses are between 6 and maybe 35 times the mass of Jupiter. So they're very akin to Jupiter, and they're at this temperature. We focused on JWST near spec data because we wanted high resolution look at the atmosphere so we could really tell what was happening in the atmospheres of these objects. So now I'm going to show you the spectra for 2 of the different objects. I'm so nervous to show this to people. It's so many people in a room. All right, you ready? Okay, thank you, Kelly. Here is our JWST near spec spectra of these 2 objects. Pause for oohs and ahs. Okay, what you're seeing is a spectrum sculpted by intriguing chemistry. Every wiggle that you see in here is real, a real molecule that's absorbing light. It's real information on what would be happening in these atmospheres. It's got cloud information in it. It's got information about the anything that's happening in the atmosphere. Now, compare and contrast. I told you these things have very similar temperatures. So one of the most intriguing thing we found when we looked at our full sample was how similar these 2 objects looked to each other. We put them up on each other. You can see their wiggles are matching each other, right? It's great. But there is something different between the 2 of them. As I'm talking and pointing out some of the molecules, see if you can identify it. Because it was like a pebble in a shoe I couldn't get rid of. I was only focused on this one feature in the blue object called 1935. So starting on the right-hand side, just to give you an idea of what's sculpting, what's shaping these beautiful spectra, water and ammonia are out here at the longer portion of the wavelength. This is 3 to 5 microns, by the way. Genaro was talking about longer wavelengths than this. Austin was showing you shorter wavelengths than this. We're narrowed in at high resolution on 3 to 5 microns. Water and ammonia are out here. Move a little bit farther to the left, carbon monoxide. There's a lot of intriguing carbon chemistry in these objects. Carbon chemistry make that beautiful shape that you're seeing. And then carbon dioxide. There's more of it than we expected. The whole different press briefing I can give you on what we saw in the carbon chemistry. It's not about the carbon chemistry at this level. I'm going to talk to you about what comes next, which is that big chunk to the left here. Maybe you've seen the feature. It's methane that's shaping everything that's kind of shortward of 4 microns here. The methane it's a popular molecule. It absorbs a lot, and we knew it was there. It's why these objects are so faint out here, because methane is absorbing a lot of light, right? But if you see with one of the arrows is pointing to here, there's a bump. There's a bump, and we're JWST cycle 1, right? Like we're getting some of the first data. There's no other object for me to compare to, so our team was left to try and figure out what this bump was. So I'll zoom in to show it to you. 2220 did not have it. No other object in our sample had it. Spoiler, doesn't have it. Just this object, 1935, that was showing a bump. Now, at first, we said, okay, here's what we're going to do. We're going to go through and look at every single dither. Maybe it's an instrument thing. Wasn't an instrument thing. Then we turn to the modelers and we say, guys, let's look at the models. It's in the grids. What's with the bump? Because we did not think to go to what is now very obvious to us. Instead of the methane in absorption, which is what 22 is doing very nicely, it's methane in emission. But why is methane in emission in an object that's the temperature that you cook your cookies at, and also 50 light years away without a host star? What's going on? Well, we turned to the solar system to help us explain what was going on. So here's images of Jupiter. On the left, it's the Hubble image in optical with the ultraviolet overlaid on it. And then on the right is the JWST image of Jupiter. And you can see very obviously on here at the poles, it has an aurora. And what we saw right away is that Jupiter had methane in emission. Jupiter had the bump. So we had a great explanation. Okay, perfect. Because the other thing is, it's not uncommon. It's not the big shocker of the world that a brown dwarf has aurora, but every other aurora was identified with a radio emission seen in the object. This was the first time that we saw this spectral indication with methane in emission, which again, we didn't know to look for it. So it took us down a bit of this investigative road. Because then the other question is, why does Jupiter have an aurora going off? Well, it has a sun, it has the star. So does Uranus, so does Neptune, so does Saturn, so does the Earth. We have aurora, right? Our object does not have a sun. There is no sun to help out in the process. But what we discovered in trying to figure out what the relationship that Jupiter has with its methane emission is it has a second contribution, and that is from the active moon Io. And Saturn has a contribution from Enceladus as well. That does not mean that we're declaring that we have found an active moon, but it's one of the explanations that can help us figure out why this methane is in emission. Okay, so the conclusion is I've shown you JWST spectra of 2 different objects that are near clones of each other. They have rich, amazing chemistry, showcasing how great JWST is. 1935, though, showed us something we'd never seen before, which is methane in emission in a cold compact object outside the solar system. And we speculate that the auroral process is causing the feature, but without a star to contribute, we have to speculate on what might be the contributing factor there, which is where we landed an active moon or maybe another internal process that we're trying to identify. Thank you.
Thanks. Hey, how's everybody doing? I'm Dakotah Tyler. I'm a PhD candidate at UCLA. I study exoplanets,
And today I'm going to tell you about WASP 69b and this enormous tail that it has trailing it. So over the past 30 years, we have found over 5,000 exoplanets. These are extrasolar planets, just planets that orbit stars other than the sun. And that's enough to do some demographics and see what is the distribution of planets like in our galaxy. And one of the big takeaways that we found is that most sun-like stars have a planet between the sizes of Earth and Neptune on an orbit less than 100 days, so closer than Mercury. Now, curiously, we don't have a planet like this in our solar system, which is interesting, but not what this talks about. Furthermore, not only are the most common planets these super Earths and sub-Neptunes, we find very few planets in between those two sizes. So it's like nature is just making super Earths, sub-Neptunes, and not really any size planets in between. We call this the radius gap, this lack of planets in between those radii. And also, you'll notice on this plot in the top left, the hot Neptune desert. There doesn't appear to be many Neptune-sized planets that are on really short orbits. So for some reason, these small gassy planets are not being allowed to exist. And we call this process mass loss, something that's going on. These planets are actually losing their atmosphere, they're losing mass and getting smaller. That's what I study. So we wanna study this mass loss process. Now, the problem is a small planet will quickly lose its gassy atmosphere. So how do you study the process in real time? You can use hot Jupiters. So hot Jupiters present a unique opportunity to study this mass loss process and like catch it in action. That's what we did with WASP 69b. It's a hot Jupiter. It's about 1.1 Jupiter radii, and it's on an orbit of 3.9 days. So it's very close to the star. It's going around quickly. It's getting bathed in radiation. You know, from the ideal gas laws, when you heat up a gas, it expands and then it can escape. So we got these transits of WASP 69 crossing the disk of its star. And you can see here in this plot what the helium absorption looks like over time. So as you move up in the plot, we are going through time, and then on the x-axis, this is the wavelength. So the feature that we're looking at is a helium feature centered around 10.833, 10.830 in vacuum wavelengths. But what you can see is that over the course of the night, there is increased helium absorption. So what you would expect to see on this plot, if there was just a small shell of helium that was outgassing from this planet, is that this bright absorption feature sort of hugs those two lines there, which are the dotted lines or the deep core of the helium feature. But you can see that after the transit ends in this post-transit sequence at the top, there's continued absorption hours after the transit actually ends, and it's being shifted, it's being blue shifted, right, into a shorter wavelength, which indicates that it's moving towards you. So there is some helium that is detached from the planet that is accelerating towards you, towards us, the observer. We're able to estimate a mass loss rate here from this amount of helium that we detected for one Earth mass per billion years. So that's quite a bit, but for a hot Jupiter, it's really not that much. This planet is like 90 Earth masses in total. So here's an artist's interpretation of exactly what that looks like. So you've got this massive planet that's orbiting the star very, very closely, and it's spherically ejecting its mass. It's losing its mass. Now, that planetary outflow is coming into contact with a stellar wind from the star. Stars have their own wind, their own particles that are coming off of them, and that actually reshapes this outflow into a really long tail, a comet, like a comet. And just for scale here, some numbers to think about. This gas is being heated to about 10,000 degrees. It is in a tail that is nearly 350,000 miles long. The tail is being accelerated towards us at about 50,000 miles per hour. So this is an extreme environment. And if you're ever considering retiring, I would suggest that you do not consider retiring on this planet. Now, interestingly, this planet has been observed before. This was not the first time even that the tail has been detected. In 2018, there were some observations taken with a different instrument, Carmenes, on a smaller telescope. And Nortman et al. 2018 found that it actually did have a tail. And you can see here on the left, this plot, it's a similar plot to the one that I showed earlier on the right, but they detected a small amount of post-transit absorption. I tried to circle it with the red. So for about 22 minutes, there was some extra absorption, which translates to a tail that's maybe 2 planetary radii long. And you can see a clear difference in our observations for over 2.2 hours. We see this tail that's getting closer to 8 planet radii. So you would ask, why in the course of 1 year would the observations change this much? Like, why would the tail look so different? And one thing to remember is that these were taken with different instruments. So it's possible that there's some instrumental variability there. In fact, we attribute most of the variability to the instrument. Keck has a large diameter. It has a large dish, so you can just collect more light. And in astronomy, if you didn't know, more light is better. So we think that most of it is instrumental. However, we can't rule out stellar variability. The types of variability that would affect an observation like this, we don't really understand in stars other than the sun. So it's kind of hard to get a handle on exactly what type of variability is going on within the star itself. But these are really interesting, and it highlights the importance of observing objects with different instruments, because we looked at this object with different instruments and we saw different things. Some of the takeaways here. So we were able to definitively detect a tail of helium that was at least 7.5 planet radii. We converted this into a mass loss rate of 1 Earth mass per billion years. Significant, but not catastrophic for a planet like this. And we attribute most of that variability to differences in the instrument and telescope. However, we can't rule out other forms of stellar variability that could have caused, what we saw to change. And again, this just highlights the importance of observing objects multiple times and with multiple instruments. Lastly, I want to thank my collaborators and the Keck team for making this research possible. Thanks.
Hey, thank you all. Those are all fantastic presentations and very interesting stuff. I love exoplanets. Okay, so let's begin with Q&A in the room.
Hi, my name's Ethan Siegel. I am with Starts with a Bang. My first question is for Jackie. Jackie, this is really cool. When you see these features in W1935 and not in W220, I would agree that this suggests that perhaps there is a tight orbiting companion around W1935 that might be worth looking for independently. Have there been any RV or transit studies of W1935 to see if there is in fact some sort of companion to it?
So the 1935, prior to this JWST spectrum I just showed you, was only a photometric. We only knew it photometrically. These things are so faint. They're at the edge of what's possible using any instrumentation on the ground for sure. So we have a radial velocity as part of this result as well. These things are faint. I don't think I emphasize this enough. These are so stinking faint, so faint. JWST was an absolute requirement to measure it. So this is really the first exposure the community has had to this object with this JWST spectrum. Our team is hopefully proposing to look for the companion, but we'll need JWST to do that. So it's going to have to come in a future cycle.
Hi, Clara Moskowitz with Scientific American for Genaro Suarez. Can you talk about why it's interesting that there's more of these clouds at the equator than the poles? And is that what we expect based on our understanding of clouds? Do the planets in our solar system have more clouds, or are these sandy clouds so different from what we have that we don't know what to expect?
And the distribution of these clouds that are more at the equator than the poles is what we expect from modeling, from general circulation modelings of these clouds. This is due to the rotation of these objects. They are rotating, so clouds accumulate close to the equator. And it is important because these kind of clouds have been detected recently in exoplanets. We know of one James Webb observation of an exoplanet with these kind of clouds, but that's only in one object. So these clouds affect the way we observe these objects. So we cannot understand completely these objects, these clouds from that exoplanet observation, but we can do that with brown dwarfs. We have tens of brown dwarfs with clouds, so we can understand those clouds from brown dwarfs and then to extrapolate that knowledge to exoplanets.
Cool, thank you. And can you just explain a little bit more what a sandy cloud is? I'm picturing a cloud with a bunch of sand flying around in it, but I don't know if that's right.
Yeah, it is. Okay, in the atmospheres of these objects, the atmosphere is of the hottest brown dwarfs is sufficiently hot to have all the material in a gaseous like stage. But when the atmosphere cools, some of those gas molecules can condense to form like dust grains. So those grains can then accumulate to form like clouds similar to clouds on Earth, but in this case made of silicates. That is the main composition of like sand. So yeah, these are like clouds of dust or silicates.
Thank you.
This is Monica Young with Sky and Telescope. I have a question for Dakotah Tyler. I'm sorry if I missed this, but I was wondering, you were talking about the mass loss rate being 1 Earth mass per gigayear. Is that enough to turn this planet into, to change the format, to make it like a rocky world eventually, strip the atmosphere?
Yeah, great question. No, so, this planet is about 90 Earth masses. So at 1 Earth mass per gigayear, it's not going to be stripped before the star itself dies. So it's safe from that. But there are planets where that does happen, particularly those smaller planets, those subneptunes.
Hi, Ethan Siegel again. Dakotah, I have a question for you this time. I noticed when you showed the absorption spectra or the absorption versus time for WASP-69b, there was a feature about just maybe 100th or 1,000th of a percent over to the left, right? This little green absorption feature, just a tiny bit to the left of the helium. And I was curious if you had an idea, it occurred only during the actual transit itself. If you had any idea what that might be, could it have been an isotope of helium or an anti-tail or something else?
So are you talking about like an isolated dot, like pixel in the plot?
You showed helium absorption in green. And there was a green feature to the left, at slightly shorter wavelength.
And was it like isolated? It was like a little island kind of?
It was a little island.
Yeah, so that's probably some noise, some variability in the data.
You don't think it's real?
I need to see the exactly what you're talking about. But if I'm thinking that I'm getting what you're saying, then there's just some noise in the data. But for what I'm imagining right now, it was all helium that was sort of around 10.833, and then as you moved up in time, it was getting shifted as you went further and further. But I'm not familiar with like any other feature around there that it
I'll follow up with you after.
Okay, yeah, definitely. Let's talk about it.
All right, I've got a question here for Genaro. This is actually from 2 people, from Bill Waller of the Galactic Inquirer and Rick Lovett. How do you know the inclination of a brown dwarf?
Good question. It is very hard actually to know the inclination of a brown dwarf we need three parameters. One is the rotation period of the object. The other one is the projected rotational velocity of the object, and the other one is the radius. So to obtain the radius, we need like different spectra or different observation that covers a broad wavelength range to have a precise estimate of the radius. For a period, we need an object that is variable, and then from the light curve of the object, we can estimate the rotation period. And to know the other parameter, that is the projected velocity, we need a high resolution spectra to know the broadening of the features in the spectra. And then from that broadening, we can estimate how fast or how slow the object is rotating. So there is a lot of spectroscopic monitoring to measure the inclination of one object.
Great, thank you. I have a question for Jackie. This is Carrie Hensley from the AAS. Mine is a nomenclature question about what to call a terrestrial world in orbit around a brown dwarf. So since it's neither a star nor a planet, do we need a third word that's neither planet nor moon?
So this jargon question pops up on social media every now and again. What do you call a brown dwarf orbiting another brown dwarf when one's really low mass too? What's the word planet mean? Does anybody want to answer that? Because if you do, I'll give you $1 million if you got a good. I actually don't like the word planet either, because it's very frustrating, especially on the brown dwarf side, where we have so many objects that are banging on the door to really be called planets. So my preference is just to call everything a world. You might have noticed that Genaro had that on his talk. We were saying extrasolar worlds in order to avoid the controversy of it, because there's no good word, I think, is the answer for whatever it would be to have our object, 1935, which you saw the low mass of it, is 6 times the mass of Jupiter. There are exoplanets that are called exoplanets that are larger than that. So the whole thing's a mess, people.
Hi, Calla Cofield from JPL. I was just wondering, I guess maybe for Austin or Jackie or anybody who wants to chime in, if any of your results actually tell us anything new or give any new hints about the formation process for brown dwarfs.
I can talk about that a little. So one of the exciting things for us, especially on the brown dwarf formation side, is before our discoveries of the 89 new benchmark systems, there had previously only been on the order of about just over 100 benchmark systems that had been known, and a lot of them were much more closely separated to their host star. And so this is a huge increase in the number of very widely separated brown dwarfs. And some of them are actually a little bit difficult to explain how they got that widely separated. We don't expect some of them to form at those distances. So there is going to be some work needed to explain exactly how some of these brown dwarfs did form. So we're pushing the boundaries there, at least.
I have one more question. This one's for Genaro. Genaro, I wanted to ask you, you showed the relationship between clouds and color and inclination of the planet with respect to us. And I was really surprised to see that there are plenty of planets, plenty brown dwarfs that are oriented to us equator on, you know, at that 90-degree orientation and at those high inclinations. But then when you get down to below 45 degrees or so to the polar ones, you only have 3, and they don't go down below about 20 or 30 degrees. Do we have any idea what's going on and why we would have so many brown dwarfs that are equator on to us and so few that are pole on to us?
Good question. My idea is here is it that we have a result from a collaborator that the variations of these objects is higher when we see the equator. So the amplitude of those variations is bigger larger when we see an object equator on, and the variation are smaller when we see close to the poles. So I think that it's this is related to the sensitivity of instruments, that we need more sensitivity to detect variation from an object view pole on compared to when the object is equator on.
Well, just to help on that one too a little bit, because that whole sample, it also comes from our research group. We had to have rotation rates for all of those objects. And so that's the variation. You know, there's only so many objects that are going to show you some sort of change in them so that you could monitor and get a rotation period out. So that's a rotation period sample that Genaro was showing. It's a harder thing to get variation on, yeah.
Monica Young with Sky and Telescope again. This question is for Jackie Faherty. I was wondering, I think you mentioned briefly that an active moon is one explanation of the aurora. Could you go into some detail about some of the other alternatives?
Yeah, I mean, we're not saying it's that. We don't know what it is, but the active moon is like a lovely, enticing, but not necessarily the explanation. I turned to the solar system, and frankly, I feel like I walked into drama that's happening in the solar system, because it's discussed in the solar system as well. And I'm relying on this being an interdisciplinary result where we can talk to the solar system people and understand, well, what are they saying? Because the thing with, for instance, Jupiter, Saturn, Uranus, Neptune, they also have too much energy in their upper atmosphere. So for them, the suggestions are a gravity wave, maybe, that's pumping from the inside out. That is an explanation that's offered. And for us, okay, we can offer that. But the problem there is that more things would have shown to be in emission. We didn't see the ammonia in emission, for instance. And then something else could be some other interaction with plasma. We're trying to find the plasma source that could contribute. So there could be some burping in the interstellar medium that contributes to it. You don't need an active moon for that to happen. So that the solar system isn't necessarily helping us with that at that front, but that's another speculative explanation that we come up with for this. That's two for you.
I have one more question. This would be for Austin. So it's inspiring to get so many people involved, citizen scientists, in searching these WISE images, but it also makes me wonder, why is it necessary? What's about the WISE images that requires human eyes as opposed to some automation technique that's used in other surveys?
It's a great question. So one of the great important things about the WISE space mission is that the photometric bands that were chosen were actually chosen also specifically to highlight the coldest brown dwarfs. So in the colors that you can get the differences between wavelengths in the WISE images, brown dwarfs will stand out very strongly. Another great thing though about the WISE images with the human eye aspect is that a lot of the brown dwarfs we're trying to discover tend to lie, as Jackie was talking about earlier, at kind of the edge of what you can detect. And so you can do this same study as we did by finding companions, just doing like a cross match between different catalogs and finding if their catalog velocities, the numbers match up. But with these objects being so faint, it can be a little bit difficult because they might not be as reliable. And so the human eye is just very, very adept at finding motion. And especially in such a large data set, citizen science projects have proven very useful in the past for these really large data-driven projects.
Any other questions in the room? Any online? Okay, then let's thank our speakers one more time. I'd also like to thank their PIOs for helping prepare them for this. I'd also like to thank our sponsors, which are on the banners outside. Our next press conference will be this afternoon at 2:15. It will be on high energy phenomena and their origins. So we hope to see you then. Thank you.